Okay, so what we started with in the investigate were these, right? What do we do with this? We held on to the string and let this thing go in circles. So let's think about that and let's talk about some of the questions with that. So let's back up. What was the definition of speed? How did we define speed? What's that? Distance divided by time. Then we talked about another word called velocity. What was the difference between velocity and just speed? Velocity includes direction. Okay? So let's keep going just to refresh ourselves. Then what was the definition of acceleration? Not the formula. You could use the formula, I guess. But what's the definition of acceleration? A change in, not speed. Change in velocity over what? Over some amount of time. Okay? So let's go back to our car. How would you characterize the speed of this car as it goes around in this circle? Constant, right? The whole point of these cars is they just go in a constant speed. There's no gas pedal, there's no brake pedal. Once you turn these on, they just go round and round and round at a constant speed. What about the velocity, though? So wait a minute. This car is accelerating? Think about what you're saying. Is this car accelerating? Hold on. So wait a minute. What was the definition of acceleration again? Change in velocity over time. And what was the definition of velocity? Speed with direction. So is this car changing velocity right now? It is, right? What's changing about this constantly? The direction on this is changing. So it must be changing velocity as well. So if we have a change in velocity, what do we also have? Just by definition, if we have a change in velocity, what do we have? Acceleration. So this car is constantly accelerating. And that's the hard part to think about because, no, man, that's a constant speed car. It just goes round and round at the same speed until the batteries wear off. How can that be accelerating? Again, this is where in physics we need to be precise with what we're talking about. Yes, that car is experiencing acceleration as defined in physics. No, it doesn't accelerate if we're thinking about how we think about acceleration, how we've always thought about acceleration until literally you started a physics class. Yes, because the direction is changing, that means the velocity is changing, and just by definition, a changing velocity is acceleration. So yes, this is accelerating. So now let's think about why. So if we have, where's my rolly chair? How can I get this chair to accelerate? Push it. Ran into the table, but whatever. So to get this chair to accelerate, I had to push this chair. A push or a pull is defined as what? A force, right? I had to apply some force to this chair to get it to move. As soon as I let go of the chair, what force takes over? Friction, and it does what? That makes the chair slow down. Right? So the velocity, to change a velocity, is an acceleration. And to create an acceleration takes a what?
Force.
Some kind of force. So now let's go back to our car. So we've decided this car is accelerating, right? What direction is the acceleration?
Around.
Okay, so hold on, I'm glad you said that. Is it accelerating in a circular direction?
No.
If it was, what would be happening to the car?
It would get really fast.
Yeah, it would speed up round and round and round. So it's not an acceleration in the same direction as the motion, correct?
Yeah.
If I let go of the string, what happens to the direction of the car? It'll go straight. So in order to curve, in order to have an acceleration, what is the force we are applying to this car?
The string.
The string. We're holding on to it, right? We are pulling the car toward the middle of this circle. That is the force that we are applying. Now in this case, it's just hanging on to this string, and that force is making this thing go in circles. So like I did with the chair, how were the direction of the force, when I push this, how did that impact the direction of the acceleration? The same? Was it different? The same. So if the force on this string was a pull toward the middle, what direction is the acceleration of this car? A pull toward the middle. The direction of the acceleration of this car is also pointing toward the middle. And it's important that you realize it's pointing toward the middle no matter where this is, right? So at any given instant, this is pointing toward the middle. If the car is right here, that is pointing this direction. If the car is right here, it's pointing in this direction, right? It's always accelerating toward the middle of that circle. Now, in your problems, right, it kept talking about roads and cornering and whatever else. I think it was investigate number, what was the number on it? Number 3, where you had to like draw a car turning to the right. Well, turning to the right is definitely not turning in a full circle, right? That's just kind of a, I don't know, in this case, what, a quarter circle? Yeah. But as you go through that curve, right, what direction is that acceleration? What direction arrow should you have drawn for number 3?
Towards that way.
Correct.
Yeah.
An arrow toward the middle of the circle. So let's switch this to here. All right, so here we have a circle. Here we have, I guess we'll just use a block for the sake of the same as the investigate was. So we have our block. And when we had our block, you know, I switched this, and now I got to switch it back. Oh, hey, welcome to the show. It's amazing. Hope you guys looked great. All right, so here we have the lab that we did, where we had a block on this table, and we spun this around. So right now, what force is acting on this block?
Centripetal force.
Okay, so yes, that's the definition of the thing. But describe what force is acting on this block as I spin this round and around. Why isn't it flying off this table? Friction. So what direction is the friction force? No. Gravity is down. Friction is resisting motion.
So the opposite way would just spin it.
Direction. What direction is the friction here? How is the friction force similar to the string for the car? What is the friction force providing?
It's just staying in place.
Correct? Yes? All right, so let's play make-believe. Let's say this was not a wood table and a wood block. Let's say this was an air hockey table, like an air hockey surface, where there's almost no friction at all. And I spun this. What would happen to the block? Would it circle like this if there was no friction? No. What would the block do? Off it goes. Or it wouldn't move at all, right? So in order for this to work, there is a friction force pointed against or back toward the circle, just like you would have with the car, correct? Friction is essentially just like this string where friction is hanging onto that block. The force of that is pointed inward. So what happens when I speed this up? Eventually, what's going to happen? It's going to fly off. Why?
Because it's going to have more force on one side than the other.
Sort of.
The movement's going to outweigh the friction.
So think about this. As I speed this up, right, what force is no longer going to be strong enough to hold on to this block? Friction, right? And then what direction, if I don't have enough friction, what direction does the block go? Outward, right? But basically, it doesn't actually go out. It goes straight at the moment that you lose the friction, right? So let's think about how all of this works, how it worked in the problems. So if this block is moving, what direction does it want to keep moving? If we're in a circle and we just take this snapshot. Right now, let's pretend this is rotating and we stop this at a moment in time. We just take a snapshot. What direction does the block want to keep going? If it's spinning this way, what direction does the block want to keep going? Straight, right? And then what force do we determine was acting on this block? Friction. And what direction is the friction? Inward toward middle. And if you sum up those forces, right, it wants to keep going, but the friction is holding it, it will just continue around in the circle. Right? Now, as we speed this up, which of these two arrows is going to get bigger and bigger?
The straight one.
Yeah, the straight one. Eventually, this arrow is going to be more than the friction. And when that happens, what happens next? The block goes straight off the table. At some point, as you speed this thing up, the inertia of that block is enough to overcome the friction force, and the block will go flying off. Right? So this is the concept of what we're doing. Anytime something is moving in a circular direction like this, it is changing direction, and if it's changing direction, there must be an acceleration. For an acceleration to happen, there must be some force. And we call those two things, one is centripetal acceleration, and one is centripetal force. Those are both physics words that are in your text anyway. But this is kind of the concept of what is happening. Okay? So because concepts are never enough, let's do some math. So what did we measure when we were doing the investigate? What was the measurable thing? This was 6A. If you guys want to look on your investigate, it should be a page or two before what you're doing. What did we measure in 6A? What did we measure?
How long is it on for?
Okay, so the premise of 6A was rotate the block at a speed that it does not fly off, right? Rotate the block at some velocity, at some number of revolutions, at some whatever, where the block stayed put, kind of like I was doing a moment ago. So somebody give me your data for 6A. 17.97. But what was that? That was a number, that's a seconds number, but what did that represent? What was the rest of the question? How long it took for, you're on the right track. How many? 10 revolutions. Now, when you're putting data for an investigate down in your logbook, I would prefer you to write this instead of, I saw a lot of logbooks that looked like this, 6A and 17.97. An improvement to this was the logbooks that said 17.97 seconds. A better improvement, a full description of what you're measuring would have been to put 17.97 seconds for 10 revolutions. Because invariably, and you guys know this by now on these investigates, you're probably going to need that data for number 7 or for number 8 or for number 10 or whatever the investigate is. So make sure you're being thorough with what exactly that 17.97 represents. Right? So now let's keep going. Let's make this useful. Right? And in this case, we had two different, I guess, units that we were using. One was revolutions per second, and the other one was the number of seconds per one revolution. Both are valid. One is time per revolution, and one is revolutions per some amount of time. And now, depending on the question and depending on what you're using them for or what some other question asks you, both of these are, I guess, valid or interesting ways to think about whatever we're talking about. Right? And so to solve this out, we simply plug in what we have. So 17.97 seconds for 10 revolutions. And this one would be 10 revolutions per 17.97 seconds. So what's the math on these? This one I can figure out pretty easy. This one not going to be done in my head. 0.5. Point what? It's kind of ugly, but whatever. So both of these data points are useful. And again, it depends on what we're trying to measure next. Right? And I think it was number 7 in the investigate where it started asking you for another measurement. What was that measurement? Who remembers? Speed?
Yeah.
All right, so let's get rid of this thing. I guess we can use it for a second. All right, so let's... what were those two numbers? Somebody read them back to me. It was 0.56. 1 point what? 0.56. What were the units? 0.56. What was the unit for that one? And what was the 1.79? Seconds per revolution. Okay? So now the next thing we have to calculate here is speed. And this is where we had to use a little bit more math. Right? So we have the block spinning around the circle. Circle is turning, let's just say this way. And now we're going to try and figure out what the speed is of this block. Right? Or the velocity, if you want to think of it that way. We're trying to get the speed of this. So we need some more data points here. We have our block here. What did you have to measure for this?
The radius.
The radius of what?
The circle. Like, one part of the middle to like of your block.
Okay, yes. So we go from the center to, I just measured it from the center of my block, and you get some radius for this circle that the block traces out as it goes round and round in a circle. Hi.
Hi.
Welcome.
Can that student take that with me today?
Sure, yeah. Which one? The quiz, the test, the...
What, she needs more than that?
Oh, yeah.
I think we're talking about 2 different kids.
Maybe. But whatever it is, yeah, we'll figure it out. Send me an email.
Yeah.
Send me an email.
Thank you.
Oh, yeah, yeah. All right, so as this thing goes round and round in a circle, the path that it takes depends on the radius of the circle that it is following. What's our formula for velocity? Distance over time. How do we figure out time? Just to be clear on this. The time of one revolution. So which of these two things do we want? The 0.56 or the 1.79? 1.79 indeed. Seconds. Now how do we figure out distance? We're going to use circumference of what circle? Of the whole disk? Just to wherever the block is, correct? So let's call this 21.1 centimeters. Just to make up a thing. How do I figure out the circumference of a circle? C equals 2 pi r. C then equals 2 pi times 21.1. All right, so what do I do with that number? That's my distance number, right? So 132.5 centimeters, velocity equals
74.02.
All right, so what's my unit here, though? Centimeters per second. Do we ever really use that? No. What should we convert this to? Meters per second. How do we do that? Divide by 100, right? We're at centimeters. We could do a T-chart for this, but I'm just going to divide by 100. Equals 0.740 meters per second is the velocity of our block. Now, when and if a question like this were to show up on, say, a quiz tomorrow, just hypothetically, I'm going to expect all of this stuff. Depending on what data you might get, I'm going to want all of this, including a drawing of what we're talking about with things labeled like the radius or whatever. You're going to have to do the math from up here, perhaps, wherever that was, where a thing rotates some number of times in some amount of seconds or whatever. But this is the degree, and this is what I would want to see on this question, how to answer this question. Then somewhere in here, you're going to do this. Yes? The question will be set up similar to the problems in the Physics to Go, which you'll see are laid out kind of the same way. A thing rotates this number of times in this many seconds or whatever.
How many questions are there?
Yes. I don't have that data figured out.
Like a page?
Hmm?
Like a page?
Yeah, it won't be a lot.